Hello, everyone, and welcome to Lab Manager's Ask the Expert interactive session. My name is Mary Beth DiDonna, and I'll be introducing this discussion on decarbonizing labs, filtration solutions for clean air and compliance. I would like to extend a special thank you to our sponsor, ERLab, whose support allows Lab Manager to offer these digital events free of charge for our readers. Our moderator for this interactive session is Scott Hanton, Group Editorial Director at Lab Manager and a lab management professional with decades of experience. He'll be having an interactive conversation on fume hood benefits and sustainability features with Jesse Coro, Director of NA Operations at ERLab, as well as Lisa Greenfield, National IAQ Specialist at ERLab. Everyone, thanks for joining us. Scott, maybe you'd like to start us off?
Well, first of all, thank you everybody out there for joining. This is a really cool opportunity to get insight from real professionals in this space. And this is designed as a question and answer, and so we're going to jump right in and get the first question on the floor. So here's our first question. Can you explain the critical role of filtration in maintaining indoor air quality, specifically in laboratory settings?
I certainly can. I'd first like to show everyone the importance of the air we breathe, and I have this demonstration behind me to really show the critical nature. Many of us walk into most lab spaces taking it for granted with every breath we take, not realizing the exposure that we're exposed to every single day. We breathe 8 to 10 liters of air every single minute, and as you can imagine, that adds up quite quickly as we're in the labs about 8 hours a day. And if we walked in our labs and we could visually see the pollution like you see behind me here with the smoke and the laser show we have going on, this is what labs look like. If we could only outline the molecules that are present in the air, or even the particles that are present in the air, or even in just an office space, we would be very reluctant to enter those zones. So that said, ventilation is extremely critical. One of the challenges that labs have today is how do we reduce these overall emissions? And really today it's about how do we add more air? We need to add more air change rates. The problem is most laboratories are starved for air. Why are they starved for air? Their air handling units can't really produce more air that they're asking to demand those air handling units to provide. And that's because of ducted fume hoods. They're taking out a tremendous amount of volume of air, and they have to make that air up. And it's impossible to just add more air changes, therefore adding proper dilution into the labs. With filtration, we can provide a solution that is not dependent of the building's infrastructure, completely independent, and it works to add equivalent air change rates. And we have to make sure that we comply with ASHRAE 621 as well as ANSI Z95 standards when it comes to ventilation. But we also have to consider the decarbonization, right? How do we decarbonize these labs? How do we decarbonize these labs? It's very challenging to do, especially because of the air that's processed. And if I look at just some quick calculations, typically labs operate at about 6 air change rates per hour. On a 10,000 cubic foot lab, so 1,000 square feet of space, that's going to average to be about $280,000 a year in energy spent and about 1.8 million pounds of CO2. That's going to be generated from that lab. Now, we know most laboratories are much larger than that for sure, and therefore that cost goes up exponentially. So again, we have to really look at ventilation from a very tailored approach, not just from the outside air that we're bringing in, but also how can we think outside the box and incorporate filtration as part of the solution. And again, to mitigate the risk of exposure, because one thing we know for sure, as you saw from behind me, we wouldn't want to enter these labs if, again, we had dosimeters on us and we knew the types of exposure we were exposed to every single day.
Thank you, Jesse. I really enjoyed your demonstration. That was really clever, and it helps us see exactly what's going on in the air around us. All right, let's jump to the next question. How does the ASHRAE 241 standard influence laboratory design and operations, particularly in controlling infectious aerosols?
It's a great question. I'm actually going to allow our expert, Lisa Greenfield, to answer that question because she's really diving deep into the ASHRAE 241 standard. So, Lisa?
Yeah. Hello, everyone. ASHRAE some people don't even know what that stands for, so I'm going to tell you it's the American Society of Heating, Refrigerating, and Air Conditioning Engineers. And these are the folks that kind of set the standards for air quality. And ASHRAE 241 was brought into play in July of last year, and it is to be able to control infectious aerosols. So this is an additional way to remove infectious aerosols or any other kind of pollutant, really, because what it's doing is it's powering up the standard of the regular 62.1. So it's typically used in like infection risk management mode is what they call it, IRMM. But ultimately in a laboratory setting, you could use this standard all the time simply because of what you're being exposed to in this setting. What was the other part of that question? Sorry.
No, that's all right. Happy to. So it was about how does the standard 241 influence design and operations, and how is it important in controlling infectious aerosols? Those are the two parts.
Okay, well, I'm definitely not a laboratory designer, but I can tell you, just like with any indoor space, it's about how much of the air exchange rates you have going on, right? Because if you're not exchanging air, you're having buildup of pollutants. So what it boils down to is how are we getting to those air exchange rates? And are we doing it through bringing in more clean air? Are we using filtration? Is it HVAC filtration? Are we supplementing with HEPA filtration, which is part of the ASHRAE 241 standard as a recommendation to fulfill those basic parameters that they have in place? So design-wise, ultimately, you can't always, like Jesse said earlier, get all the fresh air in you need, especially if you're kicking it out, which is another great thing about our filtration system is it's not connected to the HVAC system, so it works independently.
So Lisa, one clarifying question. You know, a lot of us as lab managers learned a lot of hard lessons during the COVID pandemic, and especially about infection and things that as a chemist we hadn't thought about before. Is this a way that lab managers could have more confidence in the environment of their lab and have less of that sort of niggling at the back of your brain worry about the next mass disease event?
Absolutely. I mean, it's about preparedness and, is it going to be biological? There's always going to be something. And this ASHRAE 241 can really protect us from exposure of any kind because it's working on diluting and removing those pathogens. And I was in education for 20 years, so I can definitely tell you there was a lot of pathogens being shared. So, and this also goes by the number of people that are in cubic square feet. So there's a great math equation on this, which is not my strength. So I can provide you with the equation, but I cannot do the math for you. But it's by people, and how many equivalent air exchange rates or air exchange rates. And yes, talk about peace of mind. If you're working in an environment where you're being exposed, of course you want to have some security and affirming measures like this to utilize.
Thank you, and thanks for answering the clarifying question. Jesse, the next question is going to come to you. And it's really a comment that they're asking you to have a comment on. I don't see a question mark. So it says, I'm all for ductless hoods, but it is even more critical that these fume hoods have very good containment in order to capture and filter the chemical vapors and not have them leak into the lab room. What are your thoughts?
Great question. I was actually talking about that before this presentation. That laser show that I gave, it's actually a system that you put inside of a hood to test the containment. You typically, when you test containment of a fume hood, ductless or ducted, you would do an SF6 testing and basically release SF6 gases to ensure that you have proper containment. Unfortunately, with SF6 gas, that really doesn't give you a real true definition of how well that hood contains. You need to visually see it, just like you visually saw the pollution that was around me, if indeed that smoke was pollution. So what we've done is we've taken this fume simulator and we've put it in our hoods to make sure first that we comply with ASHRAE 110 containment guidelines, which we do. And what we see is that the containment within a ductless fume hood far supersedes, more often than not, that of a ducted fume hood. And there's a couple of reasons why. Number one is we have even distribution of airflow. What does that mean? In a ducted fume hood, you're typically pulling between 900 to 1200 CFM in a 6 to 9 inch duct collar. What does that create? It's at the center of fume hood, and that creates turbulence. So outside of that zone, you now have turbulence, which now means you potentially have buildup of the LELs. You have buildup of LELs, well, we know the risk factors associated with that. With ductless fume hoods, if you see behind me, depending upon the size of the hood, we make sure the whole ceiling of that fume hood has a fan associated with it. So on a 6-foot fume hood, we have 4 separate fans. Each fan pulls 135 CFM of air. So you have that even distribution pattern. So we don't allow LEL buildup. We process the air effectively and efficiently without any turbulence, and we make sure we don't have any back roll coming out of the front of the sash. So as far as containment, I can tell you, we could run the testing. Visually, you could see that. Unfortunately, I couldn't take this system apart and do it real time today, but I can certainly send you a video that we've done to show the containment aspect of the hoods themselves. Hopefully that answered the question or commented on it on the comments.
Thank you, Jesse. That was very helpful. I appreciate it. And I'm seeing some clappy emojis, so somebody else out there also appreciated your comment. Here's the next question. Computational fluid dynamics plays a critical role, but that is not very well understood. In the name of demand control ventilation, or DCV, many people wrongly assume that just DCV-based dilution ventilation is sufficient to ensure good IAQ. Please elaborate on this.
That's a really good question. CFD is how that air flows through the facility, right? So you could be processing 6, 8, 10 air change rates per hour. That doesn't necessarily mean you're processing that air efficiently. I'd mentioned turbulence inside of a fume hood. Same applies inside of a room. So more air necessarily doesn't mean a cleaner space or a safer space. It's how that air is flowed through the facility itself. With this halo system you see above me, and this isn't a presentation to sell the product, but why we're so effective at how we process the air is because we have, again, even distribution of airflow known as a Koyonda effect of flow. So we bring the air up, we disperse the clean air horizontally across the ceiling grid, and then it comes back and it constantly recirculates. So it's very dependent upon the room design, the layout of the design, the occupancy load to determine how many of these systems is effective. With a ventilation system, typically you have a supply and a return, and that supply and returns one side of the room and the other side of the room, and you're just moving air. You're just moving air quickly, and then you have a lot of dead zones in your facility. That doesn't occur if you apply filtration appropriately within the room or any space that you install filtration. So yes, great question. CFD is something that is well used. It's a theoretical based on how the facility is designed. And then you can also do ventilation analysis studies to determine how truly does this air move and how many air change rates am I really getting? What is the true dilution factors in many different zones within that facility? So not just the center of the room, but how does it affect the corner of each room, all 4 corners or the side or where we think there's dead zones? We can actually perform that ventilation analysis to provide an assessment to determine, okay, you don't have adequate flow rates here. We know you're processing a ton of air, but again, necessarily does not mean that you have adequate flow or CFD.
Thank you, Jesse. And I've got a clarifying question to tack on top of that. You talked about dead zones in a laboratory. Are dead zones rare and unusual? Are they common and everyday? Is it something that lab managers need to worry about?
They're very common. More often than not, we know that there's dead zones in the laboratory. You know, newer labs, when they're designed more efficiently, so there's less and less dead zones. But for sure, more often than not, we experience tremendous amount of dead zones. And again, that's where the high exposure limits are within a laboratory. And that's why when we present filtration, it's really filtration can be adaptable wherever a chemical exists in the laboratory. We don't have to rely on the infrastructure. So it's independent. So wherever we think there's a dead zone, or if you're doing a weighing process, or you're using a Bravo system in a certain location, but you just don't have adequate flow rate. You can just feel it. You know that there's pollution there. Maybe you don't feel good when you're in the zone. It's because it is a dead zone. But filtration can be adaptable and can be inserted wherever it needs to be within the laboratory.
Perfect. Thanks. Let's move on to our next question. What are the implications of increasing air change rates on a lab's energy use intensity? And how can lab managers balance the two?
So the energy use intensity with ventilation is extreme. As I mentioned earlier, for a facility to go to 6 air change rates per hour for 1,000 square foot or 10,000 cubic volume of air that's looking to process, that's about 60,000 CFM that's required, equates to around $280,000 or 1.8 million tons of pounds of CO2. How do you balance that? Again, do a ventilation assessment. Determine, you can do a CFD study too to determine where are we deficient and how could we possibly actually reduce our air change rates and add equivalencies as per ASHRAE 241 with HEPA filtration systems or carbon filtration systems or a combination of both to reduce the overall EUI on that building. So there is a balance. You still need outside air for sure. Certainly not saying get rid of outside air. We need that to comply with code and for adequate dilution as well. But that combined with filtration can certainly reduce the EUI load on a building.
Thank you. Let's move on to our next question. And that's, what advanced filtration technologies are currently available that can help labs achieve equivalent air change rates? And how do they contribute to energy efficiency?
Yes, so the advanced filtration, you can do it on a molecular side and an H14 HEPA filtration side. That's not really advanced. H14 HEPAs have been around forever. It's on the carbon side, especially in laboratories, where you have to make sure that you have first the right type of carbon, the carbon bed, and a delicate balance of airflow that runs through these filters so that we can ensure that we have proper retention, residency time for adequate retention capacities. And again, there's a misconception that if your filter fan unit that's above me isn't processing 800 CFM of air, well, it's not effective. It's not turning over enough air. That's false. Again, delicate balance. It does not take much to move air at all. These systems above me operate at about 130 if it's carbon to 170 CFM if it's HEPA. And again, it's a delicate balance of airflow. For carbon, we have to make sure that we don't push those molecules too quickly past that carbon bed. So again, we allow residency time, enough parking spots for the molecule to find a place to sit. And then with HEPA, we have to make sure we also don't process air too quickly through it. Why? You need to have proper interception and diffusion of the particles. You process air too quickly, you're not utilizing that filter to the best of its efficiency. And we have to make sure we consider ISO 14644 when we test the HEPA filters as well for efficiency and leak tests. And then on the carbon side, we have to make sure we comply with the AFNOR NFX 15211 filtration standard, which ensures that the filtration capacity is exactly what it needs to be within the laboratory. And these filters have been tested extensively. Every filter that's in any one of these products you see above me on the carbon side has been tested, 750 chemicals tested under 6 different concentrations twice, so that we know the exact retention capacity of each one of those chemicals down to the molecular gram before we've seen release not exceeding 1% of the threshold limit value. So there's a lot of tests that has to go into this type of filtration technology. It's not just adding a fan and a filter and saying, you're good to go. Here's your equivalent air change rates. You're good. We have even distribution, all set. No, there's a lot that goes into the studies of these filters to determine the efficacy of the product itself.
Thank you, Jesse. And I want to ask a clarifying question on this one too. You've talked about all this data, all these testing, 750 chemicals, different concentrations. How is a lab manager supposed to understand all of that? Or how do we know enough of it that we're making the right decisions to keep our lab staff safe?
You're going to have a professional analyze. So a professional should come into your facility and ask, what chemicals are you using inside of your lab? And provide a detailed chemical listing booklet to review it with them and say, okay, based on this information, we know we have a solution for you. Now we have to take it a step further. and we have to do a deep dive analysis, especially when it comes to fume hoods. On the halo, it's fugitive emissions, so it's not as critical to do a deep dive analysis. But when we're doing at-source capture, like in a fume hood for obvious reasons, we have to deep dive into that safety assessment of the feasibility study to determine what's being used, the quantity and the volume of chemicals, how is it being evaporated, is a chemical being heated, what is the process, what's the type of container, are you using an Erlenmeyer flask, are you using a beaker? All of that's going to associate to the overall evaporation rate. Then we determine, based on calculations, how long the filters will last. Typically, a filter will last anywhere between 24 and 48 months on the carbon side. On a HEPA side, it's 3 to 5 years. We know HEPA filters become more efficient as they become clogged, but it's about the static pressure drop and how well that fan can handle it. So there's a lot that happens on the back end to ensure the safety of the lab manager, the lab technician, whoever's in the facility, and even that discussion with EH&S to have that confidence that they're providing a safe solution for their staff.
Thank you. Let's move on to the next question. How do local regulations impact laboratory operations and design? What should lab managers be aware of to ensure compliance, and how they can find more information on local regulations?
ANSI Z95 and ASHRAE 621 are the best regulations when it comes to ventilation and design and guidelines on how to effectively design a lab in a safe manner. And then there's other regulations involved outside of the lab, because it's not just how that lab is designed. There's other regulations called Local Law 97 in BERDO, and that's not necessarily how a facility is designed, but that's more about a facility that's already built, it's already occupied. Now, how do we comply with decarbonization initiatives? So there's a lot to go into it, but when you design a lab, for sure, ASHRAE 621 and then ANSI Z95. NFPA as well, depends on the type of lab and the classifications. You have a lot of different classifications depending upon the lab. If it's an animal lab, you have AALAC, you have NSF, it's a BSc lab. So it really depends upon the lab that's being designed.
We're hearing an awful lot about sustainability these days. So the next question that came in says, what sustainable practices can labs implement to improve air quality while also aligning with decarbonization goals? And what financial benefits might this have?
So we have to take a look at labs in general and their energy use intensity. And I keep using that word, or that TLA, the 3-letter acronym of EUI. It's because labs account for about 60 to 70% of a facility's overall EUI. And they only account for about 25% of the gross square footage of usage of that space. So we know their energy burdens. So how do facilities go about decarbonization initiatives, and how do we meet those sustainability initiatives? It's almost next to impossible to do so without thinking outside of the box and implementing solutions like filtration. Taking a look at a heavy use lab that has a hood intensity of, let's say, 10 to 20 fume hoods, ducted fume hoods, and really assess, do we really need these hoods to be running constant volume? Most often than not, if it's an older lab, they may be a CV hood. But even on low flow hoods, you still have that issue of buildup of LELs. And sometimes, that sash is closed, you're not processing enough airflow, and that sash is open. You don't have enough, the control valves aren't processing the air enough or efficiently, but you think because you're in a ducted fume hood, you're safe. So we really got to think of filtration as a solution. And we have dozens of case studies where we helped and were the cornerstone to labs achieving LEED certification or even ZNE, ultimately showing that without filtration and without taking out the load of ducted fume hoods and the load of air that needs to be processed, it's next to impossible. So the only way for labs to do it today is think differently, think change, think new. I mean, this is not new technology. It's been around for over 55 years, but it needs to be adopted. And we have, again, great success stories where we've been proven the results of reducing the overall load of the building, and then therefore allowing these facilities to comply with their sustainability goals. Architecture 2030 says that you must comply or there's going to be consequences to pay. And I'm actually going to allow Lisa to touch on that, because I mentioned earlier local law 97. I mentioned Berto. St. Louis also has regulations, and there's now fines associated if facilities that are above 25,000 square feet for some states and 50,000 for others. If they're not in compliance by 2030, there's going to be substantial fines. And in fact, if they don't even have a plan by 2028, I think it is, Lisa, there's going to be fines starting in 2028. So something needs to be done, and we really got to look at change and step a little bit away from just the traditional mindset of, hey, we're going to put a chimney stack on the roof, we're going to blow air out, we're good. We need to start looking at different ways to approach the lab design, lab build-outs, and safety in the lab. So Lisa, if you could speak to local law 97 specifically, and Berto kind of piggybacks on that, and just touch on those initiatives and basically the goals that need to be achieved.
Yeah, absolutely. It's happening across our country, and it's happening globally as well. We're seeking to reduce our carbon emissions. And so we're doing that starting in our biggest cities that have the largest Class C buildings. These are usually over-ventilated, and so there's a lot of waste that's happening, a lot more emissions that don't need to be happening. So a great way that you can address not being fined is by having an assessment done, a ventilation assessment done in your facility to see, are you over-ventilating? And if you are, you can use that assessment to find out where. You can make adjustments and reassess and find out, okay, you know what? We're overventilating here, underventilating here. Let's make adjustments. And they typically find that most buildings are overventilating by 75%. So you are, there's just so much waste happening energy-wise. Financially, you end up saving money, and you're helping to reduce carbon emissions. So it's a definite win. Now it's becoming more mandatory, as Jesse talked about, with the new laws that are in place for decarbonization. I put together a whole list of cities across our nation that have initiatives that are already going and that will be up and coming. So, feel free to reach out for a list of those. But basically what it boils down to is everyone has a certain timeline that they're working on. Local Law 97 starts their fining in May. Berto for Boston is not far behind. So these facilities owners, building owners, need to be having a plan in place for how they're going to do their reduction. And doing a ventilation assessment is the best way to do that. And it's also been worked into some of these new laws that if you do this ventilation assessment that we can help you with, you kind of have the good faith of okay, we're working on making decarbonization efforts, but we haven't got there yet, so please don't fine us. And so that's good news. But definitely something that you're going to be seeing more of as we go on. It's looking like 2050 is where they want to be at net zero for carbon emissions. So a lot needs to happen in the next 25 years.
Lisa, what do those fines look like? What can you put a number on that? I know they're fairly substantial.
So local law 97, it's like $236 per ton. And then those fines go up every year. So if you haven't reduced them, it's kind of like this sliding scale. The more time goes on, the more you're going to be fined. So the less mercy they're going to have. So it's really, they can be substantial, in the millions for some of the larger buildings in New York City. So really, ultimately, it's beneficial for them to be addressing it. They typically are overventilating, so addressing that can help reduce carbon as well as avoiding fines.
Yeah, for sure. Thank you, Lisa.
A comment has come in from a listener. And again, no question mark, but Jesse, I'm wondering, maybe Lisa too, wondering what your response is. It says, as a clarification, ANSI Z 9.5 is a regulation only in California and elsewhere a voluntary standard.
Yeah, for sure. So ANSI Z95 is a standard in California, but it is a standard that you can point to as guidance. Remember, I used the word guidance before. A lot of these, like even ASHRAE 241, they're guidelines to provide a safer facility. They're guidelines on what type of ventilation needs to be implemented in order to have a safer facility. They're not written into law, they're not code, but again, all guidelines, with the exception of some states. Again, it's about the AHJ, right? The authority having jurisdiction is going to point to certain regulations that they need to follow, our building codes they have to comply with, but certain regulations that the AHJ will say you need to comply with NFPA 45 2023, or maybe NFPA 45 2019. That's written into the AHJ, or ANSI Z95. So it really depends city to city, state to state, what the proper compliance is. But I use ASHRAE and ANSI. That is typically the guidelines most people follow to provide the best way to build their facility, whether it be the ventilation system or the overall safety aspect of the laboratory. And again, I'm not a lab designer or builder, but certainly I know those are the standards that they look to and the regulations they point to.
Thank you, Jesse. That was helpful. Next question. How can effective filtration solutions enhance lab safety, particularly concerning hazardous materials or airborne contaminants?
So with filtration, again, it's at point. It's being able to provide a solution wherever a chemical needs to exist. That's the benefit of filtration. In addition to that, the level of efficiency. When we look at what the potential release could be, and that's a question that people ask all the time. How do we know we're not just dumping pollution back into my lab? And it's a very valid point. We have to, when we're doing any type of handlings, we have to guarantee effectiveness and efficiency, that there will never be release exceeding 1% of the threshold limit value of the cumulative chemicals within a fume hood, period. And how do we do that? It's part of that assessment study. But you also, in order for filtration to work effectively and to know how it's working and performing, you must have monitoring systems built into the product itself. And the monitoring systems are tied into every fan module that you see. I can actually, let me just zoom in over here. One moment while I steer this ship. So if I zoom in over here, I'm going to show you how the sensors are built in and how we can guarantee that safety. So every filtration system, again, in order to operate effectively, you must have a sensor in the fan module. So this shows you 2 carbon filters. You should always have redundancy, primary, secondary. Sandwiched in between the Oreo is that fan module. And that fan module must have a detection sensor to detect any spikes of concentration that's released past that primary stage only. But even at detection phase, because all the assessments and the feasibility study that's performed, we guarantee that even if we see a spike of concentration that's released from this primary filter, we guarantee the secondary will not see release exceeding that 1%. And that's how we're able to guarantee the safety. Now imagine your lab has rotovaps, HPLCs. You have a lot of different equipment that, for better or worse, it's outside of a fume hood. It's open bench chemistry, right? You're just on the open bench. You don't really see a problem with it because, I don't know, people aren't complaining. Well, I can guarantee part of IAQ is monitoring that room, monitoring the room air continuously. I can guarantee that that room has high emission loads, meaning your employees, unfortunately, are exposed. They don't know it. You're nose blind. You're in the lab every day. We need to address all that open bench chemistry, and it's very hard to do that when you're relying on being tethered to the building's infrastructure. So filtration, again, offers that adaptability to be placed wherever that chemical exists, increasing the level of safety in the lab, adding a layer of detection, adding a layer of redundancy, ensuring that we're not throwing pollution out into the atmosphere, allowing for potential reentrainment. Reentrainment is allowed to exist, and reentrainment is allowed to exist up to 25% of the TLV on a ducted fume hood. On a filtered fume hood, With our lab, it's no more than 1%. So again, it's extremely safe. And there is a misconception regarding the safety aspect, but it's about filtration, it's about detection, and it's about communication. It's also about obviously monitoring that air quality continuously as well outside of the hoods. So there's a lot that goes into it to improve and increase your level of safety. One thing I want to point out, and I just reminded myself as I looked on the screen here, if everyone can see that flammable cabinet behind me, and I point this out because that it is one of the most noxious areas in a laboratory. Why? Storing chemicals in these cabinets. Typically, these cabinets are on lockdown and they stagnate. You could have hydrochloric, you could have an acid cabinet, you could have hydrochloric, nitric, sulfuric acid in one cabinet, and then you could have chloroform, xylene, and name your other organic solvents in another cabinet. What happens with those chemicals? We think that they're stored in a container, they're fine. Unfortunately, they're not. You have over evaporation that occurs, and that over evaporation just sits there and stagnates. And more often than not, employee, technician will open up that cabinet and they will get dosed with high concentration loads. Now, there's one thing I haven't talked about yet. It's about the exposure limits that OSHA, NIOSH, and ACGH allows us to be exposed to every single day while at work. We all react differently to different exposure levels. So I could react differently to 50 ppm of xylene, while Lisa could react completely different. I could pass out and she could be fine. It's happened. So when you add filtration, remember, being completely adaptable to wherever a chemical exists, that little box on top of that flammable cabinet processes that air continuously so that we don't allow any type of stagnation of chemicals, and we're mitigating that risk. So now when that door is open, people can open that with confidence and know that they're not going to be overexposed. So again, a lot of benefits, a lot of value with adopting filtration as a safety solution.
Thank you, Jesse. And I liked the story about the chemical cabinet because I had my own disaster stories from my lab days there, specifically with working on amine chemistry. Next question. What strategies can lab managers employ to transition to advanced filtration and sustainable HVAC systems, but without disrupting their ongoing operations?
It's a good question, and that's really going to be a case-by-case basis. It's really it's hard to answer because it's going to be lab by lab. It's a very tailored approach, so we would have to get very specific into their process. One thing that some labs do, and many do when they're running a renovation and they're trying to adopt filtration and hit sustainability measures, or just renovating their lab, is they have what's called swing space, and swing space allows for that transitional moment in time where they're going from renovation to final build. On a swing space, and again, we have many case stories of this, typically in a trailer, but you have to continue to perform your chemistry. How do you do that? How do you do that in a swing space or a trailer? You can't add ductwork. It's impossible. Filtration comes into play where you can actually take any one of these hoods that you see, storage cabinets, whatever it may be, put it in the swing space, know that we have adequate filtration. You're still performing your chemistry. Meanwhile, you're upgrading your facility to hit your decarbonization initiatives because it's going to incorporate many different technologies, just not filtration. But while that's getting renovated, you still can work on your chemistry. And then when it's done, when the renovation's done, you literally take this hood or any of these products and you put it into the final design, the final laboratory. So that's one way to do it. But again, it's very tailored. It depends on the scope of work. But that's one way to do it. And I think the best answer I can provide.
Thank you, Jesse. I think lab managers ought to be thinking about swing space, right? If you're coming up against a renovation project or a new build, keeping your operations running through the course of that is going to require some other kind of space. All right, next question. What tools or systems do you recommend for monitoring air quality and ensuring compliance with evolving standards and regulations?
Yeah, you have to have a good air quality monitor, one that can detect CO2, NOx, as well as PM 2.5, TVOCs, formaldehyde, and the sensor should be able to provide you with an overall value of what the pollution levels are in the lab. Typically, unless you want to spend thousands and thousands and thousands of dollars, typically these sensors are going to be based on a millivolt value. So it's a potential of a millivolt setting, and each millivolt will be basically coded for certain chemicals depending on what the chemical is. And as a potential of that millivolt is changed and modified, that alerts somebody within that facility that, hey, we have an issue, we have high concentration loads, and that should be able to provide an indicator real time of that pollution load and what the impact of that pollution may be. On particles, it's a bit simpler than it is for molecules. We can detect down to PM 0.3, again, depending upon the sensor you put into your device. But you should always measure particle loads too, because we talked about aerosolized transmission and mitigation risk management of bioaerosols. Well, that's a particle. We want to reduce the overall particle load. So you should always monitor particles. You should always monitor VOCs. If you're a histology pathology lab, you should certainly always monitor formaldehyde. And then you should always monitor your CO2 levels as well to make sure. Typically in a lab, it's not so much of an issue, but when we get into educational facilities and school classrooms, it becomes more of an issue on the CO2 side. But those are the criteria on which you should choose your air quality device and make sure it communicates adequately. So you have sensing and then you have proper and adequate communication.
Jesse, I want to ask you a follow-up question about the sensors. Is this a situation where there should be continuous monitoring, or is this a portable sensor that is used to periodically evaluate space?
You always want to go for continuous monitoring, because if you periodically test for your facility, you could have false negatives, and meaning that one day, for whatever reason, you're not seeing high loads. Maybe there's not a certain process that's done, that Tuesday when it's done on Wednesday, whatever it may be. So you always should have continuous monitoring. I call it a movie. It's really a movie continuously of that air quality within your facility. And you should be able to see the sequence, run graph charts on where you see spikes. It will also help you improve your laboratory practices, because if you're seeing, especially EH&S, if they're seeing spikes every day at a certain time or a specific day, they can pinpoint as to why. Why am I seeing higher spikes during this day or this hour? What's the process that's being performed? Talk to the lab manager and improve overall laboratory practices. Again, mitigating the risk of overall exposure. So continuous monitoring for sure.
Great, thank you. That's what I thought, but I wanted your professional opinion. All right, our next question, and I think with the time we have left, this probably ought to be our last question. What emerging trends do you see in laboratory design and filtration solutions that will shape the future of clean air compliance in labs?
All those standards we just mentioned, all those laws that are now put into place with BERDO and Local Law 97, and Lisa, you'll have to remind me of the St. Louis one. All these big cities are going to follow. That's going to certainly change the way that labs need to be designed for sure. We're also seeing the trend, of adoption. People are more and more starting to adopt filtration as a viable solution for their laboratories. And of course, the sustainability initiatives, again, as I touched on earlier, impossible, I'm going to use that word, put my neck on the line, impossible to achieve in a hood intensive lab without filtration. It's just, both products, filtration and ducted, and we're seeing this trend as well, Scott. A lot of facilities and new designs are going 50-50 split. So 50% of the hoods remain ducted, 50% now are filtered, and that reduces the load dramatically. And now they have the hoods for the what ifs of the unknowns or research, and then they have the hoods for the filtration hoods for all their other type of chemistry that can be performed. So that's the trend that we're seeing right now. It is a paradigm shift. I've been with our lab 15 years, and I can tell you, over the last 15 years, it's from when I started to today, significant changes in adoption.
I want to just add to that real quick. When you're not sending these chemicals and pathogens outside, we're protecting everyone outside as well. So it's the right thing to do. And that's one of the things that I love about the product is we're not subjecting other people to those chemicals.
Well said.
Yep. Thank you both for answering a bunch of hard questions that came in from our audience, our listeners. And I want to thank everybody on the line for taking the time today to listen to Jesse and Lisa. And I especially want to thank those who submitted questions and comments, and that really made today's event a lot more interesting. Perhaps more challenging for Jesse, but a lot more interesting for me.
Thank you, Scott. Thank you, everyone. Have a wonderful day.
Thanks.
Okay, great. Thanks, everyone. So that does bring us to the end of this interactive session. We're going to put Erlab's contact information on the screen for you right now. If you have further questions about this fume hood technology and you want to reach out to them offline, they've kindly provided their contact info. So please make sure to make a note of this before we wrap up our webinar in a few moments.